Good evening, everybody. It's Monday, April 6th, and this is Nighttime Mathematics Radio. Format of the show is always the same. You can tweet your math questions in to @NightMathRadio on Twitter. I'll try to answer your questions live on the air. Now, this time we have a question looming for us before we even get started, so I'll start with the question that was asked. And this is a cute question, because this question asks us to find an integral without actually knowing what the function is that we're integrating. Let's take a look. So, this question asks us to find an integral that looks very much like any other integration problem you've ever done. In that it's asking us to find a definite integral. I'll find here in a second. It asks us to find a definite integral of a function from 9 to 4, which looks a little upside down, but should be okay. It's asking us to find this integral from 9 to 4 of f of x dx. And if this were an absolutely standard calculus problem, what you do next is we then tell you, okay, well, what's the function? But we're not going to tell you that. Instead, what the problem tells you is it says the integral from 1 to 4 of 3f of x plus 2 dx is equal to 21. And the integral from 1 to 9 of 2f of x plus 10 dx is equal to 130. So how on earth can we take those two pieces of information and figure out the integral from 9 to 4? Let's look. Now, they don't tell you f of x, so we're not going to do this by actually integrating the function. What we're going to do instead is we're going to use some of the properties of integration. And two of the biggest properties of integration are that it's linear. And what that means is two things. If I have an integral of two different functions added together, I'm allowed to just split it up and integrate each one separately. I could say that's the integral of f of x dx plus the integral of g of x dx. And if I have a function times some number, say a times f of x, I'm integrating that dx, I can pull the constant right out of the integral. And those two properties are what we're going to use to solve this problem. So the first thing to notice in that first problem is that we can pull it apart. We can rewrite that first integral as 3 times the integral from 1 to 4 of f of x dx plus 2 times the integral from 1 to 4 of dx is equal to 21. And we can't forget the other side. This is an equation. This isn't just some random bit of math that happens to be floating around. Okay, so can't do much with the first one because I don't know f of x, so again, I can't integrate it. 3 times the integral from 1 to 4 of f of x dx plus, the second one's easy, I can integrate the x, it's just x. So that's just 2 times x from 1 to 4, from 1 to 4. It's equal to 21. So 3 times the integral from 1 to 4 of f of x dx plus, at the upper bound, 8 is 4 times 2. At the lower bound, 2 is 1 times 2. So I end up with 3 times the integral from 1 to 4 f of x dx plus 6 is equal to 21. I know at this point you're still keep me saying, okay, that's great, but you still have this f of x floating around, this integral from 1 to 4 of f of x dx floating around. How am I going to solve it? And the answer is, if you blur your eyes and just look at this thing that you want to know as a variable. Because remember, anything you could do with a variable, you could do with any other random thing that's sitting around in math, as long as you don't deal with the thing inside. And what this says is 3 times something I'd like to know plus 6 equals 21. And you look at this and go, okay, this isn't a calculus problem at all. This is an algebra problem. I can subtract 6 from both sides of this equation. So 3 times a thing is 15. So again, divide both sides by 3. Oops. There. And we've now successfully integrated f of x dx from 1 to 4. And the cool thing, we've done it with no calculus at all. In a certain sense, other than knowing that you're allowed to do this with the integral, this is almost not a calculus problem. This is an algebra problem so far. Let's look at that second one. It's exactly the same. The second one said, remember, that the integral from 1 to 9, 2 f of x plus 10 dx is equal to 130. And this is, again, exactly the same problem, just with different numbers. 2 times the integral from 1 to 9, f of x dx, plus 10 times the integral from 1 to 9 dx is equal to 130. And now we can just do exactly the same steps. 2 times the integral from 1 to 9 f of x dx plus 90 minus 10 is equal to 130. Twice the integral from 1 to 9 f of x dx plus 80 is 130. Subtract 80 from both sides. 2 integral 1 to 9 f of x dx is equal to 50, because 8 plus 5 is 13. So integral from 1 to 9 f of x dx is equal to 25. Cool. Now we know 2 things about f of x. We know that copying from above, we know the integral from 1 to 4 f of x dx is equal to 5. And we know the integral from 1 to 9 f of x dx is equal to 25. But there's something else we know. We know that the integral from 1 to 9, you're allowed to split up at any point in that interval. So let's split it up at 4, because we know something about 4. The integral from 1 to 9 f of x dx. Remember, you're allowed to split an integral like this at any interior point. So that's the integral from 1 to 4 f of x dx plus the integral from 4 to 9 of f of x dx. But we know each of these 2 numbers. This is 25. This is 5. Draw a little line because I'm out of paper. So subtract 5 from both sides, and we get that the integral from 4 to 9 f of x dx is equal to 20. And that's almost what they asked us for, but what they asked us for is the integral from 9 to 4, not the integral from 4 to 9. So how do we get from one to the other? Well, that's yet another property of integrals that you know, which is that if you reverse the direction of integration, you just change the sign. The integral from a to b of some function is equal to minus the integral from b to a of that function. So the integral from 9 to 4 f of x dx is negative 20, and we're done. So the cool thing about this problem is we just computed an integral without ever knowing what the heck we were integrating. All we needed was a couple of facts they gave us, the properties of integrals, and algebra like you learned it years and years ago. This is a very cool problem in that sense. And this is Nighttime Mathematics Radio. Okay, folks, we've got nothing else really burning on Twitter, so I'm going to play music for a few minutes to see if anybody else gives any questions. So over the next few minutes, if you got any questions, feel free to tweet them into Twitter. And if not, just sit back and enjoy some of the strangest little music loops that Apple's ever devised. This is Nighttime Mathematics Radio. Welcome back, everybody. This is Nighttime Mathematics Radio. Well, it looks like Twitter is silent, and so that means it's probably time to call it to close for the night. If anyone has any more questions, feel free to tweet them in. I'll try to answer them in tomorrow night's show. Until then, in this very strange world where all the math classes have stopped, but the homework goes on and on and on, feel free to ask us for help. See you tomorrow night, everybody. Good night.